Hello friends, today we shall be learning about polynomials. This module is targeted for all the students who are currently in class 9th and all the students who wish to have a recap of this topic. For reference purpose, we shall be using NCERT Mathematics textbook for class 9th. To begin with, let us first understand the basics. What do we really mean by the term mathematical expression or simply an expression? A well-formed finite combination of numbers, symbols and operators that indicates some information is called a mathematical expression. For example, 1 minus 7 plus 3. Now this term here constitutes a certain information. This can be very well solved by BODMAS and hence we denote a number, which is very well meaningful. However, here in this term, well-formed is very important because well-formed expressions give a meaningful information. Now consider, for example, plus minus bracket 27 divided by y. This is not a mathematical expression since it is not well-formed because it does not indicate any information. We cannot calculate it. Now moving further and understanding the various forms of expressions. They can be broadly classified into 4 categories, namely arithmetic, analytical, algebraic and closed form. Now, to begin with today's module, polynomials, let us first understand the definition of polynomials. A polynomial is an algebraic expression consisting of constants, variables and algebraic operations such as addition, subtraction and multiplication, and where the variables are raised to the powers of whole numbers. Now this statement here that variables are raised to the powers of whole numbers is very important and peculiar aspect of polynomials. Now moving further and understanding the various components of polynomials. In the definition we use 3 components that are constants, variables and algebraic operations. Now constants are values that remains the same throughout in a given situation, whereas variables are values that keep on changing in a given situation as per the situation or the circumstances. Now, constants are denoted by small letters A, B, C, etc. and variables are denoted by small letters X, Y, Z, etc. Now, polynomials can be in many variables, however, we shall restrict our discussion to polynomials in one variable only. Now, algebraic expressions consisting of terms in the form of ax power n, where n is a whole number, also called a non-negative integer, and a is a constant and x is a variable. Now, here the term a is called the coefficient of the term x power n. Further, degree of the polynomial is the value of the largest exponent in the polynomial. It must always be a whole number. Whole numbers are also called non-negative integers. Understanding polynomials further by way of examples. Now, polynomials can be broadly classified into 3 categories as per the number of terms in a given polynomial. For example, monomials are the polynomials having only one term. Subsequently, binomials are the polynomials having only 2 terms and trinomials are the polynomials having only 3 terms. Now, as you can see in this table, example A and C, that is 5x and minus 10 z power 0 or minus 10 are the polynomials having only one term. Therefore, these are monomials. Subsequently, example D, x square minus x is a binomial, and example B, that is 2y cube plus 9y square minus 4 is a trinomial. Further classifying polynomials on the basis of the degree of the polynomial, we have linear polynomials, that is polynomials having degree 1, quadratic polynomials having degree 2 and cubic polynomials having degree 3. Again, in this table we can see that example A, that is 5x, is a linear polynomial since the degree is 1. Example D, x square minus x is clearly a quadratic polynomial, and example B, that is 2y cube plus 9y square minus 4 is a cubic polynomial. Friends, please note that minus 10 z power 0 is equal to minus 10. Now this is clearly a non-zero constant polynomial and the degree here is 0. However, the constant polynomial 0 is called the zero polynomial, and the degree of the zero polynomial is not defined. Let us understand some important notes for all the discussion we have done till now. A linear polynomial has the form ax plus b, where a and b are constants and a must be non-zero. Similarly, a quadratic polynomial has the form ax square plus bx plus c, where a, b, c are constants and a must be non-zero. A cubic polynomial has the form ax cubed plus bx square plus cx plus d, where a, b, c, d are constants and a must be non-zero. Now, here a non-zero is very important in all the three forms described above. Simply because if a is not equal to 0, then, for instance, in a linear polynomial, if a is equal to 0, then we are just left with 0 into x plus b, which is equal to b, which is not a linear polynomial, but is a constant polynomial of degree 0 if b is not equal to 0. Therefore, while defining the general forms of polynomials, it is mandatory to say that a must be non-zero. Generally, a polynomial in one variable of degree n has the form a0 plus a1x plus a2x square plus a3x cube, until so on we get an x power n as the nth term. Now, if in the above general polynomial a0 is equal to a1 till an is equal to 0, that is, if all the terms have the coefficients 0, then the polynomial is called the zero polynomial and is denoted by the number 0, and the degree of a non-zero constant polynomial is 0. Please note, as we have further need to understand this, only zero polynomial is the constant polynomial whose degree is not defined. Now, examples of algebraic expressions which are not polynomials. In the definition of polynomials, we have understood a certain very important peculiar aspect of polynomials, that is, the variables must be raised to the powers of whole numbers only. So, in these four examples, we can clearly see that the variables are not raised to the powers of whole numbers. For instance, in example A, we have 4x power 6 plus 2x power minus 7 minus 13. Clearly, minus 7 is not a whole number but an integer. Similarly, the other three examples follow. So these are the examples that these expressions are not polynomials. So we get to a certain important result. That is, all polynomials are algebraic expressions, but all algebraic expressions are not polynomials. Now, further moving to the relevance of polynomials. Polynomials are fundamentally expressions representing some information, so they are important in almost every field and profession. For instance, designers use polynomials for designing the roller coaster rides, since the route or the trajectory in the most technical terms in mathematics is nothing but combinations of different curves put together. Also, polynomials are used in economics for cost analysis and are also used in stock markets to study the concepts of price and time, which are closely related. Now, moving further to the next topic, operations on polynomials. Firstly, let us understand what is distributive law. It is a property given by A into B plus C, which is equal to AB plus AC, and the next form is A plus B whole bracket into C is equal to AC plus BC, where A, B, C can be numbers, variables, constants, anything. Now, moving further and understanding how addition, subtraction, multiplication and division is performed for polynomials. Firstly, we shall study about the addition and subtraction of polynomials. Let us understand it step by step. Step 1. Write down the operation to be performed in the form of an expression. Then step 2. Collect the like terms together. Now, what is like terms? Like terms are the terms having the same exponent. Step 3. Perform the operation on the coefficients of the like terms. Now, let us understand this by way of an example. Consider adding 12x cubed plus 16x squared plus 11x plus 4 and 7x square minus 2x minus 1. Clearly, both the components are polynomials. Now, as per the step-by-step guide, we first write down the operation to be performed in the form of an expression. So we write we put both the components in brackets. Now, step 2, collect the like terms together. So we get then the step 3 lastly is to perform the operation on the coefficients of the like terms. For this, we also use the distributive law. That is, we take x square, for instance, outside and write 16 plus 7 in whole bracket. Therefore, when we open it using distributive law, we get 16x square plus 7x square. That is the previous step. On doing the third step, we finally arrive at the result. This is how addition is performed. Now, let us understand how the subtraction is done. Subtraction is done in a very similar way. Firstly, we write the operation to be performed in the form of an expression. Then step 2 is to collect the like terms together, and step 3 finally is to put the operation in action on the coefficients of the like terms. Now here the only difference is in step 1, that is, we put the negative sign in between the two components which have to be subtracted from each other. Then again, by distributive law, we take the variable outside and perform the step 3 similarly. Now, moving further and understanding step-by-step guide for multiplication of polynomials. Step 1. Write down the operation to be performed in the form of an expression, and step 2 is to apply the distributive law. Here, every term in second polynomial is multiplied to every term in the first polynomial. For example, consider multiplying 7x cubed plus 5x square minus 2x plus 3 and 3x square plus 4. Then, using the step-by-step guide, we have step 1, we put both the polynomials separated by brackets, and then step 2, we take every term in the second polynomial and multiply it to every term in the first polynomial, and by doing so we arrive at the result. Now, moving further and understanding zeros of the polynomials. This is the next topic in polynomials. Consider a polynomial, say 3x minus 9. Clearly, it is a linear polynomial. Now, if we denote this polynomial by px, we have px is equal to 3x minus 9. Now, we wish to find the value of this polynomial at, say, x is equal to 1. How do we do that? We finally and simply put x is equal to 1 in this polynomial. Therefore, we get 3 into 1 minus 9, which is equal to minus 6. Therefore, we say that if px is a polynomial, then pa is the value of the polynomial at x is equal to a, which we get simply by putting x equal to a in the polynomial. Now, in the above polynomial, 3x minus 9, the value of the polynomial at x is equal to 3 is 0. Clearly, therefore, here x is equal to 3 is called the zero of the polynomial. The formal definition of zero of the polynomial includes a number c is zero of the polynomial px if the value of the polynomial at x is equal to c is equal to 0. Now, friends, note that if px is a polynomial, then px is equal to 0 is called the polynomial equation. Therefore, if we say that c is the 0 of the polynomial, then we also can say that c is the root of the polynomial equation px equal to 0. Important notes for this topic. Finding 0 of the polynomial px is same as finding the root of the polynomial equation px equal to 0. Hence, to find the 0 of the polynomial, we simply solve the polynomial equation px equal to 0. Then we get a value of x, which becomes the 0 of the polynomial. Now, consider a constant polynomial, say px equal to b. Friends, note that here b must be non-zero constant. Then, for any value of x, the value of the polynomial shall always remain b. This will never change for any value of x. So we conclude that a non-zero constant polynomial has no 0. But suppose that if b here is equal to 0, then for every value of x, b is equal to 0, then implies that the polynomial value is equal to 0. Hence we say that every value of x will be a 0 of the polynomial. Now, number 0 can be a 0 of the polynomial. Consider, for example, a polynomial, say 4x or 5x or any term. Then equating it to 0, we get the value of the polynomial as 0. Therefore, we say that 0 is the polynomial 0. Now, again, it is not necessary that 0 is the only number which has to be the 0 of the polynomial. We can have, for instance, consider a polynomial 2x minus 4. Here, at x is equal to 2, the value of the polynomial is equal to 0. Therefore, here, x is equal to 2 is the 0 of the polynomial, which is clearly not a 0, which is clearly a non-constant, non-zero constant. Every linear polynomial, that is polynomial of the form ax plus b, where a and b are constants and a must be non-zero, has one and only one 0, which can be derived by equating the polynomial to 0. Therefore, we get x is equal to minus b by a, which is the root of the polynomial equation, and hence the 0 of the polynomial px. A linear polynomial has only one 0, given by minus b by a. Please note that a polynomial can have more than one 0. Now, moving further and understanding the next topic in polynomials called remainder theorem. Recap. In division, dividend is equal to divisor into quotient plus remainder. For example, when we need to divide 15 by 4, we can simply write it as 15 is equal to 4 into 3 plus 3. Here, 4 is the divisor, 3 is the quotient, and again 3 is the remainder. In polynomials, division is carried out in a similar way. Now, let us understand how the division is performed in polynomials step by step. We shall proceed this understanding by an example. For instance, consider dividing x squared plus 2x minus 7 by x minus 2. Here, dividend is x squared plus 2x minus 7 and divisor is x minus 2. Clearly, dividend here is a quadratic polynomial and divisor is a linear polynomial. Now, step 1 includes that arrange the terms of the polynomials, both dividend and divisor, in descending order of their degrees. Now, here dividend is x squared plus 2x minus 7 and divisor is x minus 2. Step 2. We write down the problem in the standard form, which is given by dividend upon divisor. Now, step 3 is important here. Divide the first term of the dividend by first term of the divisor to get the first term of the quotient. Now here, the first term of the dividend here is x squared and we divide it by x, which is the first term of the divisor. Therefore, the result is x, which becomes the first term of the quotient. Now, step 4 includes that we multiply this first term of the quotient obtained by the divisor, that is x minus 2 here, and subtract it from the dividend, which becomes the remainder, henceforth. So, here, since you can see the entire division in summary, we take x minus 2 outside, that is, write it like divisor, then put a straight lines and put the dividend inside, x square plus 2x minus 7, and then on dividing x square by x we get the quotient as x, and multiplying this x to whole of x minus 2 we get x square minus 2x. On subtraction we get the remainder 4x minus 7. Now this 4x minus 7, the new remainder, should be equal to 0, or the degree of this remainder polynomial must be less than, strictly less than, the degree of the divisor. Here the degree of the divisor is clearly 1, which is that is of a linear polynomial. Therefore we have to continue with the division. So again, this new remainder becomes the new dividend, and the similar steps are performed so that we, till the time we get the remainder as 0 or a certain number whose degree is less than the degree of the divisor. On doing this entire division, we can write x square plus 2x minus 7 is equal to x minus 2 into x plus 4 plus 1. Here x plus 4 is the quotient, x minus 2 is the divisor, and 1 is the remainder. Now we stop the division at 1 simply because the degree of the remainder polynomial here is 0, which is clearly less than the degree of the divisor, which is equal to 1. So in general we can say that if px and gx are polynomials such that the degree of px is greater than or equal to the degree of gx and gx is non-zero, then there exist two polynomials qx and rx such that we can write px is equal to gx into qx plus rx. Here rx must be equal to 0 or degree of rx must be less than degree of gx. Please note that here the value of the polynomial at x is equal to 2 is equal to 1. Now here 2 is the 0 of the divisor polynomial, that is x minus 2, and here 1 is the value of the remainder polynomial. Therefore, in general, this is called remainder theorem. Formally, remainder theorem states that let px be any polynomial of degree greater than or equal to 1 and let a be any real number. And if px is divided by the linear polynomial x minus a, then the remainder is the value of the polynomial at x is equal to a, denoted by pa. Let us understand the proof of this remainder theorem, which is easy. Let px be any polynomial of degree greater than or equal to 1 and let a be any real number. Now, suppose px is divided by the linear polynomial x minus a. Then again there must exist two polynomials qx and rx such that we can write px is equal to x minus a into qx plus rx, where degree of rx must be less than degree of the divisor, that is x minus a. Now since degree of x minus a is 1, so degree of rx is equal to 0 here. This implies that rx must be a constant, and let us denote it by small letter r. Therefore, again, by putting the value of rx in the above equation, we get px is equal to x minus a into qx plus r. In particular, the value of the polynomial at x is equal to a, we get that pa is equal to a minus a into qx plus r, which is equal to r. Therefore, we get the value of r is equal to the value of the polynomial at x is equal to a. And here we have noted that small r is nothing but the remainder polynomial. Therefore, pa is the remainder. Hence proved. Moving further, let us understand factorization of polynomials. To begin with, let us first explain what is factor theorem. If px is a polynomial of degree n, where n is greater than or equal to 1 and a is any real number, then first point, if the value of the polynomial at x is equal to a is equal to 0, then x minus a is a factor of the polynomial px. Second point, If x minus a is a factor of the polynomial px, then the value of the polynomial at x is equal to a is equal to 0. Let us understand the proof of this theorem. Using remainder theorem, we can write px is equal to x minus a into qx plus pa. Here, rx is equal to r is equal to the value of the polynomial at x is equal to a. Now, let us first prove the first point. Suppose if pa is equal to 0, then in the above expression we get px is equal to x minus a into qx plus 0. Therefore, clearly here x minus a is a factor of px, where qx is a quotient polynomial. Now again, coming to the second point, suppose if x minus a is a factor of px, then we can write px as a product of two polynomials x minus a and gx, where gx is any polynomial. So here, putting the value of x is equal to a in polynomial, we get pa is equal to 0. Therefore, the second point is also proved. Hence, we arrive at the proof of this factor theorem. Now, understanding the application of factor theorem. Find the value of k if x minus 1 is a factor of 4x cubed plus 3x squared minus 4x plus k. Then, by factor theorem, we must have that the value of the polynomial at x is equal to 1 must be 0. Therefore, on solving the value of the polynomial, we get k is equal to minus 3. This is one of the applications of factor theorem. Now, understanding factorization of quadratic polynomials using splitting the middle term method. Consider the general form of a quadratic polynomial ax squared plus bx plus c, where a must be non-zero. Now here, suppose px plus q and rx plus s be its factors. So we can write ax squared plus bx plus c as a product of these two factors. On comparing the coefficients of the like terms, we get a is equal to pr, b is equal to ps plus qr, and c is equal to qs. Now, clearly ps into qr is equal to ac. So, in summary, factorization of quadratic polynomials using splitting the middle term method is all about finding two numbers whose sum is equal to b and whose product is equal to ac. Understanding this by way of an example. Suppose we need to factorize 6x squared plus 17x plus 5 by splitting the middle term method and factor theorem. So, by using the splitting the middle term method, we can easily find the factors of 6x squared plus 17x plus 5 and write it as 6x squared plus 15 plus 2 into x plus 5. Here, 17 is written as 15 plus 2 because the product of 15 and 2 is equal to 30, which is here equal to 6 into 5, that is the values of a and c for a general polynomial quadratic. Therefore, on opening the brackets, we get 6x squared plus 15x plus 2x plus 5, which is equal to 3 into 2x plus 5 plus 1 into 2x plus 5. Clubbing the terms together, we get 3x plus 1 into 2x plus 5. Therefore, we get the factorization by way of splitting the middle term method. Now, using factor theorem, which becomes the method 2 for factorization of polynomials, suppose px is equal to x squared plus 17 by 6x plus 5 by 6. And therefore, the original polynomial, that is 6x squared plus 17x plus 5 is equal to 6 into px. Now, suppose that a and b are zeros of the polynomial px. Therefore, we must have that pa and pb must be equal to 0. Again, x minus a and x minus b are factors of px because of the factor theorem. Now, so we have that 6x squared plus 17x plus 5 is equal to 6 into x minus a into x minus b. On comparing the coefficients, we get ab is equal to 5 by 6. Now, by using the hit and trial method, we find the possibilities of a and b such that ab is equal to 5 by 6. Here we get plus minus 1 by 2, plus minus 1 by 3, plus minus 5 by 3, plus minus 5 by 2 and plus minus 1. Also, please note that since a and b are zeros of the polynomial, we must have PA and PB equal to 0. Now, checking the values which we have just found by hit and trial method for PA equal to 0 and PB equal to 0, we get that A is equal to minus 1 by 3 and B equal to minus 5 by 2 satisfies the above conditions. So, putting the values of this found A and B values in the star equation, we get the factorization as 3x plus 1 into 2x plus 5. Note that by using any of the methods, the answer is the same. To factorize a cubic polynomial Px, that is a polynomial of degree 3, we first find a zero of the polynomial by hit and try method, that is by putting different values of x in the polynomial equation Px equal to 0. Then, the obtained root of the polynomial equation, say x is equal to a, or simply the zero of the polynomial Px, implies that x minus a is a factor of Px. This is in regard to the factor theorem. So, we can write Px is equal to x minus a into gx. Now here, the degree of gx must be n minus 1, where degree of Px is n. Here, n is equal to 3. Therefore, degree of gx is equal to 2. That is, gx is a quadratic polynomial, and using the factor theorem or splitting the middle term method, which we have discussed in the previous slides, and we can factorize gx, and thus we get the desired factorization by putting the resultant gx in the double star equation, that is Px is equal to x minus a into the factorization of gx. Lastly, let us understand algebraic identities. Now, what is a mathematical identity? An identity is an equality relation A equal to B, where A and B can be variables. Here, A and B can be differently defined functions, but the equality between the two still holds. For instance, consider a trigonometric identity, that is cos square x plus sin square x is equal to 1. Here, for x is a variable and for any value of x, the above result holds. Therefore, this is a typical example of an algebraic identity or a mathematical identity per se. Now, what is the relevance of identities, mathematical identities? Now, identities are very important in mathematics. They are helpful in computing the values without actually performing lengthy calculations and for factorizing the polynomials. It quickens our process of finding the result. Now, this slide here gives a small summary of all the identities which we need to study in this chapter, such as a plus b whole square, a minus b whole square, a minus b into a plus b, so on and so forth. The derivation of these properties or identities is easy. Now, understanding algebraic identities applications. For instance, if we need to find the product of 99 into 101 without actual multiplication, we shall be using algebraic identities to find the result. Now, 99 can be written as 100 minus 1 and 101 can be written as 100 plus 1. Therefore, by using the algebraic identity a minus b into a plus b, which is equal to a square minus b square, we get the desired result. Here, a is equal to 100 and b is equal to 1. Therefore, we get a minus b into a plus b, that is 100 square minus 1 square, which is equal to 10,000 minus 1, which is equal to 9,999. So, you can see here that algebraic identities quickens our process of finding the result without actual multiplication, which is lengthy and tiresome. Similarly, if we need to find the product or the cubic value of 999, we can simply use the formula a minus b whole cube to find the result. And that completes our chapter polynomials. Thank you.